Hello, everyone. Let's start this third session. So I hope you enjoyed the lunch. Thank you very much, CRF, for the very tasty meals. So we're gonna start this next section. It's on the disassembly and testing of MARBEL's battery pack performance and end of line. We will have 3 speeches. First one on the assembly and disassembly by Antonio Decano. Second one on the MARBEL testing procedures and results at a lab level from Daniel Koch. And no need to call the Vatican. We will talk about evil stuff, but not the evil you think about. It's more the electric vehicle in the loop by Juan José Valls. And so, yeah, first picture. So we'll start with the first one, Antonio Decano. He's an electric engineer. Then he has an MBA as well, and he was in Magneti Marelli until he joined ABL Italy. He's now a senior process engineer, former senior industrial engineer. He just joined his skills in product development for high-profile sports car clients and facilitated seamless communication among project stakeholders. His commitment to continuous improvement is evidenced through active supplier validation and contributions to lean manufacturing initiatives, ensuring operational excellence and strategic procurement partnerships. Wow. So welcome.
Thanks, Alberto, for this presentation. It was very nice, and thanks you all for being here today. Yes, it's open. So today I will show you what we did in AVL regarding the assembly of this battery pack and also for the models. AVL is a global solution provider, and in Italy we are performing also assembly of battery pack for different customers. And now we is better. So today, in a couple of slides, I will show you what we did in this month. So the first step is to load the cells from the battery storage unit. We place it there because cells must be stored at a controlled temperature and also at a controlled humidity level. Then when you finish with this operation, you can use these cells to realize the model unit, and you will see how to prepare this model starting from the cells. Let me say, you have to take the cells and read all the characteristics written on the code. Let me say the data matrix and the barcode, just to register each single cells that we test. So after a visual test, we are ready to check the voltage level, just to be sure that we are processing inside the battery good pieces. As you can see, the voltage level is measured. Then it's time to register all these values and prepare the cell for the successive assembly steps. You have to clean all the surface around the cell, and then you are ready to place the thermal pad. So the thermal pad, you have to take care on placing this component because it's very sticky, and it will stick on the cell in a faster way. So the operator is taking care about this component. This is a prototype operation, so you will have some scrap part also on the thermal pad. Then after a visual check, you can place also the second thermal pad on the side of the cell. And above that thermal pad, you will place then finally the thermal fin that will transfer the heat from the cell to the cooling system. So as you can see, this operation is very simple. It takes not so much time, and this is our prototyping operation. So the cell is finalized, quite finalized. You apply a bit of glue to stick on the compression pad, so the black part, and then the cell is finished. Successive step is to apply also a thermal sensor on it. It will be useful for the IACM to measure the temperature of the cell. So the cell is finished. You can place some protective cover on the contacts, and the cells are ready to be part of the model. To realize the model, we place the cells inside a tool. So let me say this is a guiding slit to prepare the model structure formed by 12 cells. You have to put one by one the cells inside this unit and then press it. Wait some seconds, you will see it. So once you have stick it all together, you have to compress it by a clamp. And during this operation, you have to measure also the pressing force, because you cannot press the cells above a certain level. So you reach this compression level, the required compression level, and then you can start to close the model by lateral flanges that must be screwed together. Before doing this operation, you have to apply also a thermal pad on the lower side of the model, just to transfer also the heat during the operation on the cooling channel. So as you can see, the assembly is very simple. You can stick together one by one the different parts as a Lego structure. So then it's time to place the power cable between the. So with this cable, you can have the possibility to power the BMS, because this is the power cable. Then you have to place bus bars to connect the different cells. Here is the bus bar connection, and near the bus bar we have also the specific wiring that is useful for the ICM to measure the voltage on the cells. Finally, we start to close the model, fix the lateral flange, and then extract the clamp and start with the connection of the electronic part. So firstly, you connect the electronic the carrier for the electronic ICMs. Then disconnect the model from the tool, and you bring it to another workbench where the BMS and the ICM will be connected to the model. As you can see on the rear side, there are dismounted ISCM circuits. You have to compose one by one the circuits, place it on the carrier. So the carrier is the gray part. One by one, you construct this electronic circuit. And then finally, you will connect also thermal sensors and the voltage wiring on the ISCM interface. So with this, you will be able successively to monitor voltage and temperature of the cells. Final part is to mount the BMS, connect all the ISCM chain, and then connect it to the link with the link cable to the BMS unit. Power up the BMS, and the model is finished. Simple, yeah. I think yes. So then next work to do is to prepare the battery frame, realize and test the cooling system. We want to know if it's tight enough, and then we can place all the realized models inside this housing one by one, test the isolation level between models and the grounding, then connect all models between bus bar, connect also the low voltage chain, place above each model a top cover, mount the junction box, the DC filter, and the control electronics with Supermaster communication board. At the end, we can place the cooling rail, the top cooling rail, connect it to the cooling system, and close finally the battery. So that's it. This is the simple work that we have to do. Thank you.
Thank you, Antonio. I have watched this video several times, and I can only think how IKEA could benefit from you guys just to have a video of some of their their stuff, how to build it. So thank you very much. Very interesting. Let's go to the second one. Opa, sorry. No. So yeah, testing procedures and results from laboratory side from Daniel Koch, which studied electrical engineering and information technology in a bachelor's degree, and electrical engineering for mobile systems in a master's degree, both at the THI, the Technical Institute of Ingolstadt. And since the end of 2018, he has been working in the research group of safe electromobility at THI, where he's been working on publicly funded as well as industry-funded projects. And his main research interest is on modeling and simulating of battery system. He's actually doing his PhD in THI. So Daniel, thank you.
Thank you very much. It's my great pleasure to give you a short introduction in the testing activities of the MARBEL project. So first of all, a quick look at the agenda of my presentation. I will give a quick overview of all the testing activities in MARBEL and what the objectives were. Then step by step, the different device under test levels. We have set up different test setups because of different objectives in the MARBEL project and because of different, well, I would say troubles or things going on in the MARBEL project, and finally the conclusion. So first of all, our main target of the work package for testing in MARBEL was obviously to validate and benchmark the MARBEL battery pack system and its performance, mainly also the safety, the whole package performance and the safety. And for that, we have defined some core steps, which means our main testing approach was built around, in theory, or our final wish would be to feed a lot of data and a lot of levels of data into a AI training model to get optimized test procedures in the future, not only improve the result quality of the tests, but also improve the test procedures themselves to have more efficient tests in the future in terms of testing time and also costs, especially when it comes to the safety tests, it's always a huge topic linked to the costs, how many DOTs you have and how many you can destroy. So therefore, it's our main intention to ease not only the process for the performance testing, but also for the safety. So the main challenge we had, and I bet all of you who are making tests have the same challenge every time. So once the maturity of the DOT is very low, you have the highest need of data, what you need and the information you want to get from the development you do. But as the maturity of the DOT progresses towards the end, well, it's nice to have data in the end to demonstrate, but well, you have the development already done, right? So take it or leave it, more or less. But in the end, we have a full strategy in MARBEL to get at the different stages we have of the development, our data, and to feed them in at an early stage and a progressive stage into the system we were developing. So therefore, our main overview of the testing activities in MARBEL is like this. We have started with a single cell test, obviously, once we got them. Then we have gone to a cell compound, which also includes the cooling system. First of all, a conceptual one at an early stage in the project. And then we went over to module tests, which then also included cooling system as in the final design and the BMS. And currently also an ongoing activity, as most of the testing activities are the final pack, the full pack test. So let's start directly with the single cell tests. We had the main intention to characterize and validate the few information we got from the manufacturer and see how the cells react in different conditions and how their degradation behavior is, so that we could know for the modeling and for the aging model and the AI training what we should expect from our cells in use. So therefore, we have made the classical approach of different cycling conditions, different temperatures, also different C rates, and we have made interim checkup tests to generate models from the ongoing data generation. So the approach was to feed the test data, including public and manufacturer data, into a comparison between a data-driven model, which is still also an ongoing activity, and equivalent circuit model that were parameterized in a classical way, and then deduce a potential for a test reduction in the future with the aim of easing or leaving out certain tests and reveal redundancies, for example. This is a short overview of partly the results, what we had from the single cell level tests. So we have made different conditions, as I said, 10 degrees to 35 degrees and different C rates. And we see a classical, or as expected, we see some degradation over the number of aging cycles. Those were standard charging and discharging cycles. And this data we will feed into the models we have in the project to somehow, forecast a prediction of the expected life for the whole system, including the other data I will talk about in a few minutes. So not only the performance tests were going on, but also some nice abusive tests. Colleagues from EURECAT have done some super funny things you should not do at home with the cells. And we got some results in basic the degradation behavior and also their behavior under abnormal conditions. So at cell level, the main objective of those abusive tests was to validate the main information we got from the manufacturer, and then scale to the module level. We also made some nail penetration, for example, and cell overcharging tests to see also at module level whether it's compliant to the regulations for transportation, for example, UN 38.3. Which requests certain tests to be in line with the regulation. Then, since we didn't have, at an early stage in the project, we didn't have the cooling system finalized, or the development team was still in the development phase. So we had to somehow validate at an early stage the preliminary concept. So therefore, we went over to a cell concept cooling test bench, which included the conceptual cooling system at that stage of the project. So what we did was build a module-like setup in terms of connecting two cells in parallel, and include, as we saw in the manufacturing video from Antonio, we included some thermal fins, thermal pads, and compression pads in between the cell sandwich. And we attached this to a test bench, and we drove some driving cycles in addition to a measurement for the swelling force. So this is kind of the progress of the setup. We attached a lot of thermal sensors for this, because the other intention of the setup was not only to have the degradation behavior in a module-like structure without having a module, but also to validate the early concept of the cooling system. And therefore, we attached all the elements that were in the preliminary design. and build it together in this final concept cooling test bench, where we had the two cells are here in parallel, and we have the top cooling rails connected to these cell tabs, and on the lower part we also have the bottom cooling plate, and then we have a coolant flowing through both of the plates. And in addition, here you see there is a floating plate which is connected to a force measurement sensor, so we could also monitor the evolution of the pre-tension force over lifetime. And here are some graphs we recorded in the early stages. So here we see in the blue graph, it's the force evolution during a standard cycle. So in green, we see the voltage of the cell compound. So it's a single cell voltage because two in parallel. And we see the voltage, the force curve in blue. So we can also see that sort of breathing of the cells during the cycling, charging and discharging. In addition, we not only applied standard cycles, but also WLTC cycles according to the profile that is available in the standard. And we saw that in over some cycles, so we have, sorry, this is not the number of cycles, but the estimated kilometers driven according to the WLTC. And we see a slight, but not considerable at all, degradation of the cell. So this was expected. And we had the WLTC cycling in addition to the force evolution, which showed some promising results for this setup. So that was in the concept cooling test bench. Then as the project progressed, we had the situation that we would like to now test the final cooling design, which at that stage was also applicable to the modules, but we didn't have the final packs yet. So we couldn't make a final pack test and validate the full thermal behavior. So we built a classical setup of 3 modules connected in series to get a pack-like structure. So we started at cell, then module-like, now pack-like before having the pack. And this was also now an 18S2P configuration. So we have 6 S2P per cell and 3 module per module and 3 in series. And then the intention of this setup was on one hand to have a driving cycle applied at this at the setup, know the degradation behavior, and in addition, the thermal behavior of the system. Now, as Antonio showed in his presentation, the modules themselves don't come with the cooling system equipped, not fully, because the top and bottom cooling rail are part of the housing. And we didn't have the housing since we didn't have a pack. And therefore, we attached the cooling as with the regular profiles as used in the final pack and attached it to one of those 3 modules, which then look like this in the setup. So we have 2 modules with no cooling. So they have all the elements, thermal pads and compression pads as per the assembly, but no coolant rails attached. So only this one cooling module has this cooling attached. And here we also added some additional sensors to get the behavior of the bus bars we have heard today, and also around between the cooling plates and the module to validate this thermal behavior. Then, in addition, as mentioned from Shandor today from AVL, we have also included the cooling strategy that AVL developed in this whole loop to regulate our thermal pump with the cooling strategy that AVL developed to set the respective rates of coolant flow and temperature according to the actual BMS data that is generated during the test. So a live control of the thermal conditioning. So in this setup, we have finally also interconnected the BMS and checked the communications during different driving cycles. It's an ongoing activity. Since you can imagine with different setups, there are always problems and something always changes. So we have still 8 days to go for some results. In the end, it's going to be a validation of the cooling system. And if you ask yourself whether we have gone for fast charging in this setup, not yet because of some problems, but if we do, we will remove the uncooled modules to avoid thermal problems with those. But in the end, maybe we have luck and we see for future projects that we wouldn't need this cooling setup, then we could also leave them in. So anyways, as I said, we had some results for this test setup. And last but not least, we have also ongoing activities at full pack level now that they are ready, which is mainly in the safety area of the packs for the EVIL. Juanjo will show in the next presentation. But at the safety level, we have thermal runaway tests planned, then also a vibration test with a full configuration. And after, vibration test obviously before the thermal runaway, but then our plan is to initiate the thermal runaway by an overheating of a single cell and watch the respective behavior of the full pack. And in addition, as Alberto mentioned, we have some evil activities going on. So the evil test bench will be explained in the next presentation, but this is also a validation of the performance of the system at full pack level. So finally, the conclusion for the testing is we have done many tests and we have tried, since we had many different situations in the project with the cells and also with some developments, to take at a certain stage the development phase and build a test setup around it, to have early data generated for the training of the models, and also inject or include the early phase data to the model, which could come in handy for future developments or further developments with those AI training. Because, for example, for these performance cycling tests, we have, or in THI, we have made some classical equivalent circuit models for the cells, which have been parameterized by interim checkup tests. But the disadvantage is that those checkup tests are very time intensive, and you have to stop the cycling, do the checkup test, and start the cycling again. And now we are checking if we could get maybe rid of those interim cycles without losing any quality or prediction quality of the equivalent circuit models by reinforcement learning. So this is an ongoing activity, and there's still a lot of potential for future investigations. And I think besides all those conclusions or results from the MARBEL testing, which are nice, the most important fact is that it has been a lot of fun to do the experiments, and it wouldn't have been possible if it hadn't been for the great MARBEL family. So thank you from my side again.
Thank you, Daniel. So if any of you have been working in the past in any lab, you really know the challenges you have to face to be able to just put a setup to be able to just generate one graph, no? And so thank you, Daniel, for explaining so graphically the amount of work needed, no, for a lab to be able to work on the challenges needed for the validation of a battery. Okay, so let's talk about evil. Next one, so electric vehicle in the loop. It's going to be presented by Juan José Valls. He's a mechanical and in automotive engineer with more than 20 years of experience in design and project management in the automotive sector. He's currently working as a senior project manager within the battery systems department in IDIADA. And he's an industrial engineer with a mechanical specialty that joined IDIADA in 2016, initially as a powertrain integration project manager since 2023 in battery system department. Okay, so Juanjo, you ready?
Should have painted my face in red. We ready to present the EVIL project, but it's not the moment. Okay, so what is EVIL, electric vehicle in the loop? So first of all, I'm part of IDIADA. For those of you that does not know, IDIADA is an engineering service company. Mainly, we cover all the development phase of the vehicles, combustion or electric vehicles, motorcycles, passenger cars, or heavy duty. And also we have a lot of experience in electric vehicle development, both at component level, system, and complete vehicle. Okay, so the focus of this project for IDIADA was the development of this new procedure of validation of a complete system, a powertrain electric system, okay, under real world conditions, following a driving cycle and with different temperature environmental conditions in order to reproduce in a easy and fast way the real conditions of the complete powertrain. Okay. So the concept presented in the MARBEL project was to mix or unify e-motor, e-powertrain in a test bench, dedicated test bench, connected directly to a battery in a dedicated test bench for the battery testing. Okay, in this way we can validate the complete powertrain, okay, with all the auxiliaries, including the cooling system, auxiliaries, DC converters or 12-volt systems, and also the charging performance of the battery. Okay, so the MARBEL project would supply a battery pack. Okay, that we have already we have seen outside, and we have another sample in our facilities, including the BMS, the cooling circuit, the charging, and the junction box as innovations within the battery. Okay, IDIADA should provide the battery test bench and also the e-motor test bench to connect and to validate the battery in real conditions. Okay, and also some components needed for performing this validation. So the electric motor and also the peripherals and the inverter. Okay. So for this project, IDIADA provides one of the more than 20 back-to-back e-motor test benches that we have in our IDIADA headquarters in Tarragona, Spain. Okay. These test benches are working in back-to-back configuration, E-axle versus E-axle, one working as a dyno, as a DUT, and the other working as a dyno. Okay, and they are equipped with climatic chamber, and also they are equipped with a battery emulator with capacity up to 1,000 volts, 1,400 amperes, okay, and 400 kilowatts. In this case, for this project, instead of testing E-axle versus E-axle, okay, what is proposed, and it is also implemented, is to make an e-motor configuration. So one e-motor working as a DUT connected directly to another e-motor working as a dyno. Okay. Another facility that is provided in IDIADA is the battery test bench. Okay, we have 4 test benches, climatic chambers from -40 to +75 degrees in this case, with battery cyclers, in this case 1,000 volts, 1,000 amperes. Okay, all of the climatic chambers are equipped with fire extinguisher system because are prepared to work with low maturity level batteries. So we are prepared in case of incidents. And we have also all our test benches equipped with an external cooling system. Okay, we have different systems, some commercials, some in-house development cooling systems to cool down the battery or to reproduce the conditions that the battery will have in a complete vehicle. Okay. So we have the picture, we have the 2 test benches with all the components, and we have the first issue or the first issue to solve is that we have the 2 test benches separated 2 kilometers one from the other. So we cannot put a cable directly connected from the motor to the battery because we have in the middle our test tracks, and for sure they don't want to stop working in the test track to make the work to pass a cable. So what the solution that we perform is to connect both test benches through UDP connection. Okay, and we have to update our test benches. Okay, initially we have both e-motor and the battery lab isolated. They were with close network, internal network. And we have the high voltage lab. This is the last facility that we built in IDIADA, okay, that was connected through a firewall to internet. Okay, so what we perform, what we did is to upgrade our test benches, the e-motor test bench and the battery lab, and connect to the same firewall, okay, as the high voltage, and use this firewall to control the communication between the different labs and the different to the outside also. Okay. So regarding test, as I said before, we perform a back-to-back configuration e-motor versus e-motor. In this case, we perform the test with 2 equal motors. Okay, this with these are the specs of the motors, which was 400 Newton meters and 210 kilowatts. Okay, and one is, as I said before, working as the DUT. So it is control the speed control. So it is the objective is the DUT has to follow the WLTP cycle. Okay, so we have to control the RPMs versus time in the DUT, and the second DUT is working as a dyno. So what has to reproduce is the rolling resistance of the vehicle. Okay, rolling resistance of the vehicle. Okay. So what we did is implement the cycle, the WLTP cycle in the test bench. As I said, we have on the first hand a DUT that we have to convert the kph of the vehicle. So the vehicle speed versus time that is defined in the WLTP cycle to RPM at motor level. Okay. And on the other hand, we take the data from an internal development project that we performed with Polestar. It was an internal development project for inverter characterization and calibration. We performed some cost down tests on our test tracks, and we measure the driving resistance of the vehicle. And with this data, we extract the curve of resistance versus speed. And from that force versus speed, we calculate the resistance as torque in the motor as the dyno, okay, versus speed. Okay. On the other hand, we have the MARBEL battery in our facilities. Okay, we have all the connections performed already with the battery. We have also built a switch box in order to be able to automatize the driving conditions with our battery cycle, and also charging conditions in the charging port. So we have here the drive port and here the charging port, and we are able with the switch box to automatize when the battery is empty, connect the battery cycle directly to the charging and start the fast charge activity. Once it's already charged, again connect to the drive port and continues with the cycle. Okay. Then once we have the test benches ready to start the testing, we have to communicate them and decide which are the signals that we have to communicate and how we do that. No? We have several operative signals like voltage, current, power, temperature, and so on. But mainly these 3: voltage, current, and power is the main signals that go back and forth from the e-motors to the battery lab. Okay, so we define the current consumption from the motor. We apply to the battery. We read the voltage reaction on the battery, apply to the battery emulator and the motor, and so on. Okay, and then we have another kind of signals, because are confirmation signals, that is TV status. So we decide if we are stop, if we are ready to start test, if we are cycling, if we are charging. So we have to know each test bench have to know in which status we are of the cycle. Okay, and we have 2 more confirmation signals, watchdog and handshake, that are mainly to verify that the communication is ongoing, that there is no freeze, and we keep working, but there is an error on the communication, and also to check the speed communication between the test benches. Okay, and then the final point is all the automation system of cycles, aging, driving, how when we reach the low shock value, stop, then start charging, how many fast charge we perform, and so on. This is another part of the automation that we perform in the test benches. So, as a conclusion, what we have performed is a new, would say, system level testing system. Okay, it is safe because all of its component are tested in a dedicated test bench with all of the safe security standards. Okay, for that component in especially for the battery. Okay, and it is quite flexible because we can adapt. Finally, it's easy to adapt to different vehicle conditions, so different vehicle specifications in terms of rolling resistance or aerodynamic resistance. Also, we can test different motors with the same battery, different batteries with the same motor, and it is real time. Real time because we have a small delay. We have checked the speed communication. It is about 3 or 4 milliseconds delay in communication, but it is not a problem because at the end, our battery cycles has a refreshing of 10 hertz. So it is not is faster than what our battery cycler is capable of react. Okay. So that's my presentation. Thank you.
Thank you. Thank you very much, Juanjo. So I think it is the evil. It's not as bad as no. Where are the crucifixes here? No. So this is the evil. It's a perfect example of two things, two very important things. First, you don't need a vehicle to validate realistically a battery. And second one, you don't need to have the full equipment in the same space to validate a battery. You can even have the powertrain separated 2 kilometers away from the battery. So that's the innovation of MARBEL, no? So thank you very much. Now it's time for a Q&A. So please, all the speakers, don't be shy. Okay. Okay, so any questions from the audience? No one? After lunch, no questions. When is the coffee? No, yeah, in 5 minutes. No questions? Okay, so I have a question from the audience. How many packs were assembled? So we're assembled 3 battery packs of 800 volts and 1 battery pack of 400 volts. That's the answer. For Antonio, how long does it take to build a pack, and any estimation on how it could be improved if automated?
So on a prototype level, we need approximately 2 hours to build up a model. And then for a battery pack, also I looking on a big scale, 16 hours to complete the battery pack, also with commissioning, where commissioning means testing all the electronic stuff to be sure that the battery pack is working well as required. So improvement options. I think on an industrial base, you can use a thermal paste instead of thermal pad, just to speed up the process. And this will be very useful for automation because you can dispense in an automatic way the thermal system. Also, there are also possible improvement on the connection between bus bar and cells. So the fixing method of the bus bar. Today we have 1 nut, screw, and some screw and nut, and you can think to redefine this operation by using a self-clinching nut that is more feasible, more useful for an automation. I see only this at the moment.
Okay, thank you very much. Any question from the audience? Nope. Yes, sorry.
Okay, a quick question for Daniel. So when you show the configuration of 3 modules in series, so 2 with 1 with cooling system and 2 without.
Yeah.
So we didn't discuss directly, but I ask you here
Sure.
in front of everybody, did you see any difference in behavior, in results during the first, I know, the not official tests?
Yes, well, not many tests have been going on since I built up the system, but on the other hand, I filled the whole cooling system with the one module where it has a cooling system attached with a coolant fluid and let it circulate at a set rate, so nothing changes. So you see a bit of a difference in a regular standard cycle. So no demanding cycle, but for the cooled module, you see slightly lower temperatures than for the others at room temperature. So I expect some impact between the both, especially when it comes to fast charging. Yeah.
Thank you.
Something else for the audience? Another question for Daniel. What about the swelling? So how do you measure the resultant force due to the swelling of the cells or the breathing of the cells?
How?
So how did you measure the resultant force, the swelling?
Okay, yeah. So in this concept cooling setup I showed, there was a floating plate that was connected to a measurement, a force sensor. Yeah, thank you. A force sensor that was continuously measuring in parallel to the voltage and the temperature development, evolution of the system, the force evolution. So yeah, this round device here. Yeah, this one. Thanks. So we could track the whole evolution, beginning of the cycling and end of the cycling, and in interim for the checkup test. What delta we had per cycle round, so beginning of the WLTC cycling and the end, and also the overall increase. So we saw a bit of an increase, but not tremendously. So around 10 kilograms force in general, a total increase over those measured 50,000 kilometers, around 50,000. So if that answers the question, we had a continuous logging of the force.
Thank you. Any questions? So another one for both Juanjo and Daniel. What about the aging test at pack level? How do you manage the fast charge and how do you measure the aging at pack level?
Well, as we said before, the tests are still ongoing, so we have not produced a lot of or enough cycles to see an aging effect on the battery. But the plan is to perform some capacity tests after several cycles. And regarding the fast charging, it is also agreed. Repetitivity of the fast charge every I think it's 10 cycles. Yeah.
And what happens if there is a connection loss between the benches?
Yeah, we have, as I said before, we have several signals of confirmation. Okay, in order to control if there is not a connection loss, and in case of connection loss, both test benches are automatized to stop the test and continue the test after we have connection again. Yeah.
I don't have any more questions from the audience. I think maybe I can ask another thing to Antonio. How can MARBEL's modular design help and improve the industrial process automatization?
So I think that to answer this to this question, you have to see on the design itself. As you have seen this morning and also this afternoon, the design is modular. It seems like a Lego structure. You start by assembling small pieces to arrive to the bigger one. It's very simple to assemble.
Anything else from the audience? If not, it has been an absolute pleasure from my side to be part of as a moderator of this table. Thank you very much for the opportunity, and thank you the speakers. So let's clap together. Thank you.